Welcome to Zaic Design's Guide to Industrial Sensors.
This is an inductive sensor. This is an encoder. This sensor is a limit switch, a mechanical limit switch. This is a potentiometer, another angle sensor. So this is a through beam sensor. This is another inductive proc, so you can see how tiny they can be made. This is what they call a load cell. This is also a strain gauge, and this strain gauge works exactly the same way. Push buttons are sensors also. And then we had this one, this guy. And then we have ones like this, which are just plain bigger. So this guy is also a distance sensor. This is a transmitter and a sensor, thermocouple. This one's a pressure transmitter. This is a flow sensor. They call it a soil sensor. So this is a sensor that detects pH. So this one's what they call ORP, oxygen reduction potential.
Position and motion sensing.
So initially, sensors were almost entirely mechanical. And so we had things like this guy, which is a mechanical limit switch, and still very common, very useful, and it's completely mechanical. There's a switching element inside contacts. It's still very useful, and it usually indicates things like a door being closed or something being in the correct position, but it's just on and off. It's not anything analog. This is a combination of mechanical and electrical. This sensor is a limit switch, but the difference between this limit switch and the other limit switches I showed you is that this one can actually sense repeatably down to 2 microns. So this is used typically to set the home position for CNC machines and so forth. You move till you hit it, and you'll notice it has a lot of over travel. So you come in, you hit it, and then you back off and you wait for the switch to close. And the output's electronically switched because the contacts in here, to prevent welding and damage to the contacts, is using a very, very, very tiny current, which is then amplified on the output. And that's how they get the accuracy. It's not a snap action switch. 2 pieces come together, and that's how it works. Used in CNCs and so forth. You don't think of it as being a sensor, but push buttons are sensors also. And this is a mechanical push button, right? It works with a contact block. And in this style, which is a panel mount 22 millimeter, can have multiple switch blocks on it. The green ones are normally open, and they have red ones that are normally closed, and you can stack them up and have a lot of different circuits switched at the same time. And we don't do that much anymore, because normally now we take just the signal from a single push button and we go to a PLC input, and then the outputs from the PLC can switch a lot of different things. And we can do other things like interrupt the circuit. So it was real common to gang them up in the past. But it's a push button, it's a sensor, and then we have some other kind of neat push buttons that are a little different. So this push button, these two, these are both push buttons. And what's different about them is these buttons are what they call a piezo sensor button. Piezo is a crystal that when you put pressure on it, it generates an electric signal. So both of these buttons have a unique feature. On this button, the mechanical one, I can push it and hold it down. With these buttons, you cannot hold it down. It puts out a pulse, and that's it. And so in some cases, that's very nice, because if you're looking for a signal and you don't want to see multiples, which is frequently called bounce, which you get from a regular mechanical switch, these are nice. But they're not useful if you need to be able to hold the button on. So it's a different style. Now this one also has a light built into it. And the reason for using these is these are very, very rugged switches. There are no moving parts. They are waterproof when they're mounted in a panel, and they pretty much never go bad. This is a potentiometer. potentiometer is a sliding resistor. There are two terminals on the end, a resistor in the middle, and a slider runs across it, and the resistance changes on the output. This one happens to be a 10 turn. Inside there's a coil, and as you turn it, it goes further. So you can measure more than 180 degrees. You can measure up to 10 full turns with this. It's typically used a lot for like fine tuning of a value that it puts out. And in order to read this, you either put a voltage to it or you use a current input, and it can work either way. So this is real common on control panels and things like that. It's also quite often used to measure angles on things that move. They do wear out, which is one of the reasons that you don't see them as much anymore. So then we have another angle sensor. So this one's kind of unique. This is a fairly new thing. This is a sensor that senses level, and it can sense the angle of that it's at based on gravity. So this puts out a signal, and this one happens to put out 4 to 20 milliamp signal, which is analog. And there are also versions that put out 0 to 10 volts. And with this, we can tell the angle of position of something on a vertical plane. And they also make this same sensor with 2 axes so that it can also sense tilting in this direction. Right? So you have this and you have this. This is an encoder, okay? This goes on the end of a motor shaft, and it's digital in that it produces a pulse, and it actually produces 2 pulses that are out of phase. And what that means is this is called quadrature. And by having the 2 phases out of sync, what happens is you can tell the direction of rotation and how fast it's going. The way it works is it turns on 1 channel, it turns on 2 channels, it turns on only this channel, then it turns on only that channel, and you have 4 different signals, quadrature. And by telling the sequence that they're going on, you can tell what direction something is going. So this is used to generate a signal that indicates position and speed, because you can count the pulses or count the time between pulses and get the speed of a motor or whatever.
Proximity and object sensing.
This is an inductive sensor. What an inductive sensor does is it senses metal. It works best with steel or stainless steel, but it also works with aluminum. And the advantage to this is there are no moving parts in it, and it doesn't actually come in contact with the metal that you're sensing in most cases. So these are really popular, this type, an inductive proximity sensor. And the way it works is it generates an electric field in front of this sensor, and when a piece of metal goes into it, the field changes, and then the sensor can sense that. So this is an inductive proximity sensor, and these are available with lots of styles. This is a little flat pack one. This one, which is a cylindrical, which is very popular. And you'll notice this one is flush-faced, whereas this one, which is also an inductive proximity sensor, has a face that sticks out. And the difference between them, they both work the same way, except that this one's called shielded and can be buried in a piece of metal all the way up to the face and still work and sense. This one, on the other hand, has to be free of any metal around it, or it will sense that metal. So that two very similar ones, they work exactly the same way, and they go on and off and sense a position. And then we have ones like this, which are just plain bigger. And what that does is give you more range. Again, this is an unshielded sensor. This one can pick up a piece of steel from about an inch and a half away. And this particular one is still working. It's about 25 years old and was used on a machine that this told the machine when it was at the end of a track that was several hundred feet long. And it couldn't get close to stuff, so we used a large sensor. So inductive sensors are very, very popular. And then we have, this is another inductive prox. You can see how tiny they can be made, right? And this one was being used to sense the edge of a piece of sheet metal being up against the stop. So this is a through beam sensor using light. One side shoots a beam of light and the other side receives it. And this is used with a blade or a disc that rotates through the sensor to tell you how fast something's turning or when it's reached the end of its travel. It's non-contact because of the brake beam, and they can operate very fast. The downside is they aren't very good in a dirty or dusty environment. That's when the inductive proxies really take over, because the inductive proxies are very, very dirt insensitive. So then we have this guy. So this guy is also analog, and this measures distance by using ultrasonics. It makes like a beep that's at a frequency you can't hear, and it counts how long it takes for the beep to return from an object that it sees. Works good on liquids, it works good on solids, it works good on powders and things like that. It is somewhat sensitive to temperature changes because the speed of sound in air changes with temperature. And it's pretty broad. You can't like pick up a small target with it. It's a area type sensor. If there are different heights, it's going to kind of average the height of the thing. But it's quite good at sensing pile height and that kind of thing, or tank levels. So that's an ultrasonic. And again, it puts out the same kind of signal that the PLC sees, which is, in this case, is 4 to 20 milliamps. So this guy is also a distance sensor. And this one is based on a laser. This one shoots a small laser out and then is looking with a photo detector from an angle. And by triangulating where the photo detector sees the spot, it knows how far away it is. This one happens to have a range of about 2 inches to 10 feet. So it's got a pretty good range, and it can be very, very accurate. I can get the same style, same case and all, in ones that will measure down to 10 or 15 microns of accuracy. So you can measure the thickness of a piece of paper with one of these, or a thin piece of metal. So very useful. And again, it's 4 to 20 milliamps output, puts out the same signal as all the other devices that we're showing you. So these are quite expensive right now. This one's maybe $700. Actually, the longer range ones are less expensive. The ones as you get closer are more expensive because they're much more accurate. The nice part about this is this produces a spot that's only about 1/8 of an inch in diameter, which means that you can pick up a very, very small part with it and pick that out from everything else.
Force and mechanical stress sensing.
So this is what they call a load cell. This one happens to have a rating of 5,000 kilograms that it can measure, 11,000 pounds. And this uses what's called strain gauges. There's inside this cover here, this centerpiece moves, there are fine resistors that when they get stretched, as this bends the beam, the resistance changes. And there's a set of resistors in here that cause an imbalance, and that changes the output voltage. You put a voltage in and you get a voltage out, which varies based on how much weight is on it. Now, this is a really, really common technology nowadays because it's a very simple, very robust circuit with this strain gauges. This was used for us to test a screw that was putting on a high force, and we needed to measure somewhere around 4,000 pounds, and that we used this to do it. But then this is also a strain gauge, and this strain gauge works exactly the same way. There are resistor elements in this bridge, and when this bridge deflects, it puts out a signal. The signal that this puts out and the signal that the big one put out are exactly the same. So this instrument that reads the big one and the small one is the same device. Now, this one happens to be a 1 kilogram. So that one's 5,000 kilograms. This one is just 1 kilogram. And we have one in a device we just built, which is just 100 grams. They all put the exact same output out. And this gives you, force measurement. So you can tell how much pressure you're putting on something or what something weighs. And if you see most of the common electronic scales today, this is what's inside. One side is mounted and the other side has the pan on it. And that's how the scales work. So it's a very, very simple and very robust technology that puts out an analog signal.
Environment sensing.
Then we have this guy. This is a transmitter and a sensor. And in this case, the sensor happens to be thermocouple. What a thermocouple is two dissimilar metals that put out a voltage based on the temperature that they're experiencing. And this puts out millivolts, which means that it needs an amplifier to put out the 4 to 20 milliamp signal that we're familiar with. We can also get these in a RTD resistance temperature device, a type of resistor that changes value with temperature.
Pressure sensing.
This one's a pressure transmitter. This guy senses pressure and it works with a diaphragm. And the diaphragm can be made from stainless steel or ceramics and stuff. And these are really way better than the pressure gauges that we had years ago. And the reason is that diaphragm just barely moves. It moves maybe 1,000th of an inch. And so the internal volume that you're seeing with the pressures does not change much. And as a result, these are very resistant to fouling from solids. As long as you're mounted upright, these things will almost never clog. I've used them on raw sewage, and you would think that they would clog right up. If they're on top, they don't. Put them underneath, you're done. They fill up with solids, and in fact, any place below horizontal is a real problem. So you always try to put them from on top. But again, this puts out a 4 to 20 milliamp signal. This particular one is 0 to 60 pounds of pressure. The same, what looks like the same sensor can be anywhere from a sensor that can pick up vacuum down to minus 14.7 psi to plus 14.7 and all the way up to 10,000 psi. And the other thing good about these is that the rated overpressure is like 10 times the device's rating. So this is a 60 psi sensor, but it won't be damaged by pressures all the way up to 600 psi, which is a big advantage. In the old days, what they call the board-on tube gauge, where a tube uncurled to show you the pressure, and sometimes turned a pot to give you an output. If you overpressurize them, they were done. And like 2 times overpressure would wreck them. And then you say, well, that's a lot of overpressure. The problem is you get shock values. Water moving in a pipe and a valve closes, it slams to a stop. You generate really high pressures. So that's a pressure sensor.
Flow sensing.
Then we have, this is a flow sensor. Okay, and this is something fairly new. This is a, thermal dispersion type of flow meter. So what happens is there's a heat source and there's a temperature sensing element down in here. And this is put into a pipe, and how fast the liquid or air or gas sheds heat determines how fast it's going. So the velocity of the water or air going past the sensor, it tends to cool the sensor. So that cooling effect is how it judges how fast it's going. It's not as accurate as some of the other types of flow meters, paddle wheels and mag meters and such. But the reality is lots of times you don't really care how accurate it is. What you care about is repeatability, and it's quite repeatable. Repeatable meaning that when that flow happens again, you get the same value out of the sensor. And again, 4 to 20 milliamps. And this particular one can also do switching, where it can act as a flow switch, where it puts out an on-off signal and so forth. You'll notice how long the stem is. That's because you can insert it into a pipe that's that large, or it can go into something that's only that long, and they make the stems in different lengths. But when we purchased this one, the short ones weren't available, so that's why we wound up with this one. We're actually going to read this in a pipe that's only a half-inch in diameter, and it will work just as well. You calibrate it for the size of the pipe that you're working with. You get the cross-section area of the pipe, and that's how you calibrate them.
Specialized sensors.
They call it a soil sensor. And essentially what it is the porous material. And this one is actually sensing basically soil moisture. It's probably using electrical conductivity of a porous material, and that based on how much moisture is present, it changes. This one also happens to be I²C. And I bring up the I²C stuff because if you're out looking for sensors and you're trying to experiment, it's just unbelievable how many sensors are available now that talk to the Arduinos and the Raspberry Pis and so forth. I mean, there's tens of thousands. I say tens of thousands. There's probably 1,000 different sensors available for all kinds of things. And basically, the difference between the stuff that they sell for the Arduino for $20 and the industrial sensor for $200 is primarily the technology is the same, but the robustness of the signals and the casings that they're in and such is where the big difference in cost comes in. But when you're trying to prototype something, a lot of times those inexpensive sensors can be really useful, and because you can test something to see if it's even feasible to use that type of sensor. So this is a sensor that detects pH. And so pH is how you know the difference between acids and bases. And so a pH of 7 is considered neutral. Higher pH is a base. Lower pH are acids. So this is used in water applications to judge whether you need to add acids or caustics to the water to get a neutral. So it's used both in wastewater and in clean water processes. And it's heavily used in industry wherever they're using liquids, as pH is a very important value to measure. And of course, this is what they call a galvanometric one. And so it has to connect to a small amplifier that changes the signal into something that the PLC can read. So this one's what they call ORP, oxygen reduction potential. The bottle on the end here is a preservative liquid because these go bad if they're just sitting out in air. It's primarily used in wastewater, so it measures another factor. And then we have one that's called dissolved oxygen. It measures the level of oxygen in any kind of water, whether it's wastewater or clean water. So this is a color sensor. And this particular one talks in a format called I²C, which is Arduino and this microprocessor levels. So in order to use one of these, you have to have a device, typically an Arduino or something, to convert this signal into a level that the PLC can use, which could be 0 to 5 volts or 4 to 20 milliamps and so forth. But this has a light, shines a light on a material, and the reflected light produces 4 signals. Actually, it produces the red, green, and blue, and it also produces what's called color temperature, a 4th source, which is a combination of the 3. You'll see color temperature listed on light bulbs when you buy them now, especially on LEDs. You'll see they have what they call warm white and cool white and so forth. You'll see that they list the color temperature in Kelvin. Kelvin is based on absolute 0. So you'll see like 5,100 degrees Kelvin is like a cool white. So that's a color sensor. And so that's This is just to give you a broad idea of all the sensors that are available to us today. And so the force sensors and so forth now give robots the ability to judge how hard they're pushing on something. The laser sensor lets the robot measure distance to something it's trying to pick up. And of course, we also have vision sensors, which we haven't gone into today. The vision sensors are really coming along, but it takes a lot of processing power to do vision, whereas none of these devices, they don't involve any real computer power. It's a very low amount of computing power to use it. When you get into vision, all of a sudden you need massive computing power to do anything. As you can see, this kind of stuff is what's making the robots able to do a lot of things that they couldn't do, 30 years ago. And primarily because there just wasn't the sensors. And the sensors are getting better all the time. And it's moving really quick, really quick.
Thank you for watching Zaic Design's Guide to Industrial Sensors. For more videos like this, please like and subscribe. And to read an in-depth technical article that complements this video, visit zaicdesign.com/blog.